had a homework exercise due. Do you have any problems with that? Difficulties with that problem, let's put it that way. Few apparently have already handed it in, so if the rest of you are ready to hand in your solution, I'll take them. And I got another handout to give you an exchange, but it's not a problem. I'll keep one here and see if I take one of those moving along. Thank you.
That's really good.
Do you have any extra problem sets back there?
Any more problem sets?
Problem sets with the handout. Is there an extra handout back there?
Did you get one?
I don't think so. We just...
Well, this little handout here was simply an effort to make it maybe a little clearer what I was talking about last time. And so I'll take a few minutes to go through this if you like. I attempted to point out that the classification we made of the behavior of binary systems as far as vapor-liquid equilibrium is concerned is sort of arbitrary. There's no clear-cut, there's not a clear-cut case between those that exhibit a normal behavior, those that exhibit an azeotropic behavior, a homogeneous azeotrope, and then those that exhibit heterogeneous azeotropic behavior. Or put it another way, if you take a homologous series of alcohols with water, as the first page of this handout indicates, you go through a rather progression of behavior, starting with a normal behavior through those that form homogeneous azeotropes, and then we get into the area where we have maybe a limited region of immiscibility, and we get the appearance of two phases, and then as we get greater molecular weights farther up this series, the region of immiscibility is larger, and until we finally would reach a state where we can, or a situation where we can consider that there's no solubility in each other, using octanol here as a sort of an illustration of that. It would still be a heterogeneous azeotrope, but you can calculate, estimate the composition and the boiling point from the principle of total immiscibility, whereby we assume that the vapor pressure of each component is merely its vapor pressure in the pure form. Now on pages 2 and 3 of this little handout is examples of how you can apply this principle I just mentioned, the principle of steam distillation, or principle of immiscible components of a binary system, to estimate the composition of binary azeotropes of weakly miscible mixtures. So in the first part of that, I've given you the vapor pressure data. In this case, for various values of the vapor pressure of the pure component, the corresponding temperature is given for water, pentanol, hexanol, and octanol. So then you can take that data and assuming complete immiscibility, and this the relationships that we previously discussed, calculate the vapor composition if completely immiscible. So first I've done it here for pentanol and water, and it comes out that the azeotrope would have a mole fraction of 0.195 if we had a completely immiscible system, and or on a mole percent basis about 19.5%. The reported azeotrope, however, is about 14.5 mole percent and the boiling point of 95.95 degrees centigrade. So there's some discrepancy there, and presumably the major discrepancy is the fact that pentanol is not completely immiscible with water. There's a slight self-solubility. So the next page we did it for hexanol, and it would calculated mole percent, and the azeotrope would have, when I worked it was 10.3, but the reported value is only 5.5, so the agreement there is not so good. Then I went ahead and calculated for octanol in water, where at about 99 3/10 degrees centigrade, the vapor pressure of octanol is 18.3 millimeters of mercury, and in water is about 74.17, giving a total pressure of 760 millimeters of mercury, or 1 atmosphere, from which then the composition of octanol in the vapor phase would be simply the fraction of the vapor pressure contributed by octanol to that of the total pressure, 18.3 over 760, or about 2.41% octanol, mole percent. The reported value for this is 99.4 degrees centigrade boiling point and 1.5 mole percent. So it's reasonably close. The rest of that page is a little summary of that data. And then in the last page is a plot of where you would go about to find the vapor pressure, or the temperature rather, at which the vapor pressure is equal to some desired pressure, such as atmospheric. This is an attempt to make it a little more clear what I tried to sketch on the board in the previous periods. So you see here the vapor pressure is plotted on a vertical scale versus the temperature on a horizontal scale, and so you in the region here around 100 degrees of boiling point of water, of course, the actual vapor pressure contributed by octanol is not very much in terms of millimeters of mercury. But anyway, if you plot it here, then plot the vapor pressure of water, and then if you want to know the total pressure of the two systems together, you simply add this distance, this vertical distance to this one, and plot another curve. Now, in reality, a situation like that, we're only interested in a rather small range here, so it would be more accurate if you only plotted, let's say, a 10-degree temperature range here. The vapor pressure is on maybe 100 millimeters. But anyway, this shows how you do it. So, are there any questions about this handout? Now I want to say a few words about sources of information on vapor-liquid equilibrium, and how it's obtained. Well, I said before that there's two ways of obtaining it. One is by making estimations based on physical properties of pure components. And that, of course, was the subject of this exercise here that you were to hand in today, assuming an ideal mixture. And I've mentioned before that more elaborate or elaborated methods, which can become very complicated, can be used and are used to estimate the vapor-liquid equilibria for various systems, introducing, as I said before, the activity coefficient, which and other factors. Now, there are whole books devoted to this subject. One of the most authoritative and is on your reference list, titled Vapor-Liquid Equilibrium by Hala, Pick, Fried, and Willem, published by a group at the Institute of Chemical Technology in Prague, Czechoslovakia. Now in the early part of this book, they discuss in much detail principles we've mentioned already, that we've been discussing, methods of calculating from a theoretical basis, and finally a discussion in here about the direct experimental measurement. That's the second method, direct experimental measurement. Question?
If we were having a problem understanding some of this, would that be the book to go to, or could you recommend another one, maybe that's less detailed, more elementary?
Very elementary.
Well, this one is somewhat more involved than you would normally be concerned with, unless this was your professional field of study to concentrate on. However, if you're interested in vapor-liquid equilibrium, and for example, a good summary of experimental methods, this is the best one I know of in one particular place for determination.
What about
The general books I gave you on distillation, like Van Winkle and Hengstebeck, would have some on this, and
basic material?
Basic, and be probably even more complicated than you even need for this course. But but if you want to read further on it, look in those first. A book like this is an excellent book, however, for getting into it in great detail. So as I say, that there is still interest in being able to calculate from theoretical principles vapor-liquid equilibria, because, as I indicated before, the probability that the system of two components considered together as a binary mixture may not have been studied. I happen to find, looking here in my notes, a little thing that I mentioned before about the probability of having a system having been studied. If you wanted to assume that we have 500 compounds, that's a very small number of organic compounds to be considered in the whole gamut of organic compounds. But if we want to consider that how many combinations of those 500 compounds as binary systems you would have, how many did you want to guess? In other words, we can say we got 500 organic compounds. There's literally thousands of organic compounds, of course, but let's say 500 might be of interest. And how many combinations of two would you estimate they might have?
2.5 times 10 to the 5th.
Well, it comes out to be 124,750. Exactly. If you remember from algebra, one of the ways of calculating the number of combinations of n things taken P at a time. It's a little formula. Well, I'll put it down here. M combinations is equal to factorial N over factorial P times N minus 1 factorial, where M is the number of combinations and N is the number of things, and P is the number taken at a time. So applying it to just a consideration of binary mixtures, we'd have that M is equal to 500 factorial. That means 500 times 499 times 498, on so on down, divided by factorial 2, P is 2. In other words, we take 2 here, and we took 500 here, and so we want to know how many combinations are, times N minus P, which would be 500 times 2, or 498 factorial. Of course, this is equal to 500 times 499 times 498 factorial. So that's divided by 2 times 498 factorial. And of course that cancels, so you actually have 500 times 499 times 499 divided by 2, which is 124,750. Well, by some criteria, that's not an astronomical number, but it represents a pretty large number if you're talking about things that have been experimentally determined. Now, it's true that a lot of the substances that are much more commonly, a lot of compounds that form binary mixtures that are very important, such as ethyl alcohol and water, have been studied many times, so you really don't have to worry about making any theoretical calculations for ethyl alcohol and water. But interesting enough, in some research we were doing a few years ago, we found that there was no vapor-liquid equilibrium data reported for, I think it was isobutyl alcohol and ethanol. So here was one important higher alcohol and ethanol that there's no reference to in the literatures. Well, we didn't calculate it, we actually determined it because we were in the process of making the measurements at that time. But anyway, this sort of illustrates the reason why there's still interest in doing things on a theoretical basis, because the possibility of having all the data in hand from experiments is rather remote. Some of these equations that I've mentioned, such as the Margulies equation and Satchard's equation and so forth, which have introduced activity coefficients in these complicated expressions, are frequently employed to check on the consistency or the reasonableness of some experimental data. In other words, applying them backwards. So it's very commonly done. So some of these theoretical considerations have very practical, pragmatic value, even though you're not applying them in the direct calculations. Well, so much for that, and a few words about how we experimentally determine vapor-liquid equilibrium. Well, of course, all it requires is being able to obtain a sample of a vapor that's in true equilibrium with a boiling liquid under a given pressure. Now, if you're most often we're concerned with 1 atmosphere pressure, but sometimes we're interested in determining values at some other pressure. So you have to have some system in which you can regulate the pressure at times. But anyway, in the simplest case, you would, for experimental determination of vapor-liquid equilibria, You might, and this is sort of the system that used in maybe 100 or 75 years ago, was simply to take a large flask that might hold 10 or 12 liters, something like that, a relatively large flask containing a mixture of the compound to be studied, and then taking off of some of the vapor, bring it to boil and bring it through a condenser, and collecting some of the distillate. Now, in order to ensure that this distillate was in equilibrium with this, that they would take, first of all, a large volume of the liquid, so that by taking off enough sample to measure here, you would not have significantly affected the composition of the liquid, you see. Very large in reference to the distillate. Large volume of liquid. In respect to the volume of the distillate. So that'd be one essential, and the second essential would be to have good insulation. Good insulation, especially of the upper part of the boiler, because if this is exposed to the air and the boiling point temperature in here is significantly above room temperature, you'll get condensation of the vapor on the walls, will cause the heat leakage to the room, the air, and so this causes a certain amount of rectification or revaporization. So if you have condensation going on here, you would get probably an enriched mixture. You would get an enriched mixture with respect to the more volatile component. So anyway, these are subject to the criticism that you're likely to get some error due to either heat gain or usually heat leakage to the surroundings, and also required a rather bulky setup. But nevertheless, a lot of our data, old data in the literature, is based on determining equilibrium by some system not much more elaborate than my sketch here. And still, with some of it very good data. Careful experimenters can take into account whatever there might be the errors and minimize them. So the second type of this might be the first type. We might call this a large batch or pot, large batch or pot still. That's about all it is. And the second type that I want to mention is what's called a recirculating still. Recirculating equilibrium still. Now there are various designs and schemes that have been used. In this book I was just mentioning here gives drawings of all the important ones that I've ever heard about, so that I think it's very complete. But in principle, I'll just draw here a little sketch. It's you simply take a boiler like that, but it doesn't have to be as large now. And they frequently have insulated walls, or at least in the upper part it might be insulated, vacuum jacketed. And then we might have some sort of an internal heater here. And here'd be the liquid phase in here. This might be a vacuum jacketed. In fact, vacuum jacket for insulation. Not only vacuum jacketed, but silvered to keep out radiant effects. But silvered or mirror finished, you see, though. In other words, I'll show you one, and probably next week in the laboratory along this style, and we can look at it in detail. But anyway, some elaboration here to make it to avoid heat losses to the air. And then in principle, it simply goes off to the vapors goes off here. You usually have a place to put a thermometer in so you can read the temperatures. And the vapors conducted over to a condenser. Well, the condenser may stick up like so, and either be open to the atmosphere or open to the pressure regulating system. And then the condensate flows down. Sometimes we have another cooler on here to keep it cool. This is condenser. And then, through some, whatever design is, it returns back into the pot. The liquid returns back in here. Well, then you have a sampling device so that you can draw some out here. So in other words, this liquid here is brought to a boil and allowed to vaporize, and the vapor goes off and is condensed and flows back, and simply recirculates back into the pot. If you start with a given mixture here, start it up, and of course it will be a discrete volume you have to use. Maybe it's 150 milliliters, something like that, a couple hundred. That'd be a typical size of liquid that they take here. And if you put in a mixture of two volatile components, one of which is more volatile than another, well, of course the first vapor given off will be higher in the more volatile component, and so that will cause the liquid to start to decrease in quantity. So it'll be changing. And then, of course, after any appreciable amount circulated, the liquid over here will be weaker in the more volatile component, so the vapor given off will be weaker. But anyway, if you keep circulating that, it'll finally come to an equilibrium or a balance. And so you can estimate when that's approached by watching the temperature. The temperature will change, usually go down for a while, and then it may actually go back up, because you can get in the system where you get a little cycle effect where you get a depletion here initially, then you get an enrichment again when this vapor gets all pushed around. So, but anyway, you simply keep it in circulation until primarily by experimental checking, you've figured out what the time is necessary to reach equilibrium. In other words, you take a typical example of the system you want to study, and then you might run it for circulating it for 1 hour, and then 2 hours, and then 3 hours, until you ascertain that you've run it sufficient time to get the constant values. Then you could apply more or less those conditions for subsequent mixtures, so you get a curve to plot, you see. So anyway, that's the way the data is obtained. Frequently, the apparatus, various designs are not considered sufficiently precise to measure boiling points to the critical or accuracy required in the literature. And so sometimes other apparati, devices are used for measuring boiling points of mixtures, where you know an exact composition, and you do use a special apparatus to determine boiling points. But in principle, you could, with the same apparatus, you can determine the boiling points of a mixture and the composition. In other words, after it's been circulated a while, then you stop it and draw off a sample of the distillate from here, and from a sampling device over here, draw off a sample of a liquid which is in equilibrium with it, and analyze for the components in question. All right. A book like this does not give the actual vapor-liquid equilibrium, but it gives one of the most extensive collection of references ever found in one place. This whole back part of the book is simply an index of compounds that you might want to look up the vapor-liquid equilibrium data for. So, in other words, the way you do that, you look in here, let's say, here's methyl alcohol in the left-hand corner, a column. And then it gives all the other compounds that have been studied with it. Here's methyl alcohol and ethyl alcohol, and here's ethyl acetate, and here's isopropyl alcohol, and toluene, and so forth, water. And it gives a number here, which is the references. You can get an idea of how important the substance may have been by, here the combination of methyl alcohol and water has been studied by, it looks like about 30 or more people that made papers to it. So those numbers then you can turn over here to the reference and find the actual reference in the literature by number. And so then you can go to the library and find it and get the information, if you can't find it elsewhere. Now, there have been some books published, collection of vapor-liquid equilibria. Here's a simple one, published about 15 years ago, probably. And I think there's more. I think there's more recent editions of this. This is 1950. But anyway, inside here are tables of data. And for example, here's binary system number 98 in this book, and it gives the references that they've used for reprinting the data, and the references in the back. But anyway, it gives here methanol and water again. Here's an example. And so here's a column of mole percent of the liquid in one column, and the vapor composition in equilibrium with it in the second column. And then it also gives a temperature, and it gives a pressure here. In this case, it's shown as 760 millimeters. You can find others here where there's other pressures given. So sometimes you can find the data in reference books such as that, such as this, or you may have to go, may have to go to the original publication of the information. Well, as I've indicated before, we're very confident of the vapor-liquid equilibrium data for ethyl alcohol and water. So much of what we may be interested in distilled beverage industries is be the behavior of minor constituents, and so I mentioned a little bit last time of how we do have data on the volatility, we could call it, of trace components as a function of ethyl alcohol and water. I gave you a couple little charts last time, one of which had to do with alcohols and one had to do with esters, I believe. It would be nice if we knew more about some of the newer compounds that we now know about and identify in wines and their volatility. We can sort of guess at it in a broad sense what their behavior would be. For example, you could take a compound like ethyl laurate, for example, and take a compound like phenethyl alcohol, both of which are important minor flavor constituents of wines, which affect the composition of distillates, brandies, or even grain spirits. And you could predict from looking up the vapor pressures and the solubility data in a sort of a broad sense how they'd behave. Well, it turns out that ethyl laurate, that's when I said ethyl laurate, which is the ethyl ester of straight chain 12 carbon fatty acid, has a very almost negligible solubility in water. It would be much like octanol, we took the example. And so if we've never, and no one's published any vapor-liquid equilibria as far as ethyl laurate and water is concerned, or ethyl laurate and ethanol solutions, where ethyl laurate is simply a small solute, less than a percent or 0.5% in the ethyl alcohol water solutions. But I can predict what would happen, and experimentally we've observed what happens. It has exceedingly high volatility in water solution or weak alcohol solutions. So that if you distill a wine which contains ethyl laurate, and the wine is, let's say, 10% alcohol, the ethyl laurate will distill over right at the start of the run, right at the start of the distillation. In fact, it'll probably all will have distilled over before more than 10% of the liquid distilled. It'll all be in the distillate. Because it has appreciable vapor pressure, it has practically no solubility in water, and it's such that it has a considerable high volatility, even 10% alcohol. But of course, as the alcohol distills out, the water percent alcohol and residual liquid goes down quickly, approaching water, and so the ethyl ester distills over very quickly. As far as that's concerned, the higher alcohols, like isoamyl alcohol, do the same, but not quite so rapidly. These ethyl esters, which are derived from yeast, as I've mentioned, distill very quickly, more rapidly than, let's say, the amyl alcohols out of the wine. We have done this in our using our batch pot still, taking periodic samples of distillates and analyze them for higher alcohols and 3 different ethyl esters of fatty acids, and so what I'm telling you is what we've observed. And perhaps a little later I'll show you a slide or a chart of some of the data we've gotten in that respect. Now, referring back to the second compound I mentioned, phenethyl alcohol, and I just picked it out of my mind here. I don't have the data in front of me, what the boiling points or the solubilities are, but I do know that phenethyl alcohol, being somewhat related structurally to ethyl alcohol, with the phenyl group substituted down the line there on the chain, has some solubility in ethanol and in water, considerably more at least than ethyl laurate, our first example. I think the boiling point is essentially as high as ethyl laurate, but the solubility is greater. So when it's distilled out of wine in a simple distillation, it does not have sufficient volatility. It doesn't have as much volatility as ethyl alcohol, so it does not significantly apparent in the first distillate. When you get down to about, well, I don't know, when you get down to lesser percentage alcohol, so the distillate is running maybe only 40% alcohol, well, then the phenethyl alcohol begins to come over more abundantly and continues to come over, and until the alcohol level in the distilling liquid is fairly low. So that's an example of how some of these properties are of interest to us to predict where they're going to end up during distillation and under different conditions of distillation. Now, I'd like to move on to a discussion of kinds of distillation and some to which we go into in some detail. I think about the first day we mentioned that we can classify kinds of distillation according to process. Into continuous or steady state types. And further subdivide that into single equilibrium stage or single stage, which we called or have synonymous names for, sometimes called flash distillation, or equilibrium distillation. Those two terms. Then we had multi-stage, or which is where we consider in a process several repeated vaporization stages, and this is generally called fractional or fractional distillation. Or rectification. And to complete our table, we can, of course, have a discontinuous or batch distillation. And further subdivide that into a single stage, which we sometimes call just simple distillation or differential distillation is sort of a technical term applied to it, differential distillation. And finally, we can have, by this scheme, of course, multi-stage here, which generally is simply called batch rectification. Or pot rectifying, or pot rectification. Well, what I want to do is introduce the discussion today of this first consideration here, and to simplify that, I will reproduce my notes here, so I'll just give you a copy of them. Save me writing it on the board again. In entirety. I might say that flash distillation may have some applications in the wine industry, but it is not a process primarily used for making alcoholic beverages. But it's worth taking a little time to discuss here, because well, for one application or potential application is recovery of volatiles from vaporization of fruit juices such as grape juice. Now, a lot of talk about recovering essences of fruits when you evaporate them, make concentrates. And there's some application of that, but anyway, many of the processes by which concentrates are made represent flash distillation or flash vaporization processes. So let's say that we have here simply, in principle, we simply have a feed material pumped into a process and usually goes through some heater stage to increase the energy. And in principle, at least, we allow this material being pumped through a stage under pressure and being heated up to a certain energy level, and then allow it to expand through a pressure valve into a chamber in which the pressure is reduced. Now this might be atmospheric pressure or maybe under reduced pressure by having applied a vacuum system to it. But anyway, we'd call this a flash chamber. And in principle then, we'd have, if this is a boiling liquid under a certain pressure and then the pressure is markedly reduced, it will boil and give off vapor, flash off vapor, because it cannot, under the lower pressure, it cannot retain the enthalpy that it has, or the BTUs per pound that it has at the high temperature, which is maintained as a liquid by having a pressure here. For example, you could take grape juice and heat it up to, it might boil at 212 or about maybe 14 degrees centigrade with the soluble solid in there. But under a pressure system, you could heat it up to 250 or 275 degrees Fahrenheit, and it'd still be a liquid because you don't, it'd still be a liquid. And so it would have a certain heat content, enthalpy as we say, appropriate to that temperature. And if you reduce it to atmospheric pressure, it can only have the enthalpy corresponding to 212 degrees. So some of it's going to flash off as a vapor. And if you reduce the pressure further, say down to a vacuum of a tenth of an atmosphere or something, well then there'd be a greater amount of it flash off. So anyway, however you do it, anyway, this would be the vapor flashed off, and of course it would be condensed, probably, and to a condensate. And then you'd have the unvaporized liquid flowing out here. So in effect then, we simply are dividing a feed stream into a vapor stream and a liquid stream, which we can represent with our those two symbols, three symbols. Yeah.
When you heat it up, you boil it, right? You take it up to boiling in the heater?
Well, that would be, of course, the that would be the maximum you could get if it's theoretically you'd have to. You might not actually have it exactly at boiling. It wouldn't be necessary. As long as you have some enthalpy that's greater than the amount it can have as a liquid at this pressure, some of it will flash off.
Well, I was wondering if this was kind of like the principle of superheating, you know, since you're dropping the pressure, and it's already been, if it's already been boiled.
Well, this could be considered superheated liquid. When it gets to this point, it's superheated with respect to atmospheric pressure, but that isn't a very good term. We use the word superheat usually applying to, well, mostly it applies to vapors that are above its saturation temperature or boiling point, but you can have superheated liquids which then all of a sudden, for some reason or other, they don't vaporize, and then if you give it a shock or something, then it'll vaporize quickly. Like that's called a bumping in laboratory. You have to have some nuclei for boiling certain liquids, so you can get superheating of liquids in the laboratory or elsewhere.
You superheat them, then you say drop the pressure or bump them in some way, and they automatically flash boil.
Yeah, well, of course, in an industrial process like this, well, there wouldn't be any problem of of retaining a liquid with the superheated in this, it'd flash off. without any question, with all the agitation involved. So, I won't take time to write, time is up, but I won't copy down what's on here. But you see now, we can write this overall balance, like start out here. Feed is equal to vapor plus a liquid. And then we can write a component balance on that by multiplying each stream by a symbol which represents the concentration of the volatile component in the liquid. And then the second step here, or third step, was introducing symbol small f to indicate the fraction vaporized. The ratio of the vapor to the amount to the feed, or V over F, represents fraction vaporized. It's not necessary to do it that way, but that's just a little simplification. So you end up with a simple expression there, number one, that y is equal to f minus 1 over f times x plus x sub f over f. Now that's the relationship between the composition of the vapor and the residual equilibrium liquid. That should be. That's an error there on that the right-hand side of the page. The relationship between the composition of vapor and the residual equilibrium liquid instead of vapor. Make that correction. And it's based on or a function of the process conditions, in this case, the fraction vaporized. Now that is equation of a straight line if we assume that the fraction vaporized, F, is a constant, and of course the feed composition would be constant, so this is a fraction of a straight line which relates the equilibrium composition of the vapor to that of the equilibrium liquid as a function of the amount vaporized.
Could we go back 1 second to Fy equals xf minus x plus fx? You said you multiply each component by a symbol meaning the vapor, the partial vapor pressure?
No, going back to the second equation that we wrote there, which is called component balance, we multiplied each stream by the symbol which represents its composition. V represents the rate of flow of vapor, and Y would be the composition of a component in the vapor. And F represents the amount, either mass or pound moles or whatever basis of the feed, and X sub F represents the composition of a particular component of interest in the feed, X sub F. If we're talking about, let's say, alcohol, well, Y would be the concentration of alcohol in the vapor, X sub F would be the concentration of alcohol in the feed, and then X would be the concentration of alcohol or whatever the volatile component is in the liquid. In the liquid that's in equilibrium. And so anyway, you can see what we're doing here. We actually utilize this expression to calculate or determine, if we like, the concentration of Y and X for a given fraction vaporized. And in order to do that, we have to have a second relationship besides this one based on the process conditions. And the second relationship, of course, is the vapor-liquid equilibrium. In most cases, this is graphical data or plotted or tabular data. So this means to solve a problem like that, we usually have to resort to a graphical solution. As down at the bottom here, use the XY data graphical method, or for very limited cases, many times this is adequate, we can use a simple relationship that Y is equal to KX, our old Henry's law type principle. For very dilute solutions, usually the concentration in the vapor may be a straight line function of the amount in the liquid, and so we can substitute in, for example, even we can do that for ethyl alcohol, up to about 1% alcohol. We can say that K is about 10.8x. Okay, maybe next time we'll have a problem to illustrate this.